Today I'm going to talk about something a little probably different than what we've been hearing about kind of all morning and a little bit this afternoon. So I'm an associate professor at ECU at Brody School of Medicine. And then I've also run our Mass Spec course down there. So what I'm going to talk to you today about is all of the different biophysical techniques we use to look at some of the protein structure, function, regulation activities that we have. I didn't want to give the organizers this actual full title of what I'm going to talk about today, because then I thought they might want to rescind my invitation, since I realized as I started putting the talk together that redox is at the very, very end. But really, we're going to talk about protein motions, intrinsic disorder, allosteric, substrates, redox switching, structure, why people are wrong, why we're right, and pretty much everything else under the sun. And we'll see a lot of the techniques that people have been talking about all day long. So CD, unfortunately, no AUC because we still haven't gotten it. We're quite right yet. But CD, DSF is on here. And just to give you the why. Everybody wants to know the why. Why do we care? Why are we studying all of these things? So when you start looking at neurodegenerative disease, because that's what our lab is really focused on, the incidence of this is increasing, right? Aging, number one risk factor. That is it. It is aging, and you can't stop aging, right? So when you're looking at it, 1 in 6 people over the age of 65 are going to be diagnosed with some sort of neurodegenerative disease, Alzheimer's, Parkinson's, Alzheimer's related dementia, Lewy body dementias, all of those kind of fall under that category. The number right now, 2020, is 52 million people in the United States. Baby boomer population is getting older. Okay, so they're starting to age. By 2050, that number is going up 47%. So we're going to look at 82 million people are going to be diagnosed with some sort of neurodegenerative disease. And really, again, that's all because the population is aging. But it's not just in the US. When we start looking at worldwide, so this is our worldwide numbers. In 2022, it's about 55 million people with some sort of dementia, which is just this broad, huge term for basically covering all of these neurodegenerative diseases. By 2050, we're looking at 139 million. That's a lot of people. When you look at costs, so these are the cost for just Alzheimer's and Parkinson's alone. This is cost of the US economy. So this is Medicare, Medicaid. This is also lost wages for caregivers. This is hospitalizations. Looked at 345 billion in 2023. By 2050, that's 1 trillion with a T. It's a lot of money as well. But here's the really scary fact, right? So you think about these diseases, think about people showing the symptoms of memory loss. They're kind of, starting to get a little bit of tremors. Maybe mom's not remembering where she parked her car or put her keys. Dad's having problems remembering to shut off the oven when he leaves the house. All of those symptoms, though, by that time we're starting to see the clinical manifestation of that. We're looking at already having a bunch of neuronal death that we can't get back, right? So anywhere estimated between 50 and 60%. These diseases start somewhere between, they're estimating now, 12 to 20 years beforehand. Now, whether that's in your gut, whether that's somewhere else, whether that's from chronic inflammation, we're not sure yet, but we know it starts way earlier. And here's the problem. There's no cure, right? So these are progressive diseases that just get worse and worse and worse. And all we do is treat symptoms, okay? So all we can do is give someone levodopa for a while to make them stop with their tremors. Or we can give them certain anti-anxiety meds. We can just make people comfortable. And hopefully some lifestyle changes, if we can catch it early enough, will help slow progression, but we have no cures. One of the reasons that we don't have a cure is because we really have no idea how these diseases start, what is responsible for these diseases, and really how to fix them. So this is just the big, huge, broad overlap of what our arching slide of what our lab does. What we're doing is basically every project in our lab kind of comes down to this one fundamental question. So what causes proteins, things like tau, alpha-syn, alpha-beta amyloid, or the protein that we're going to talk about today, transglutaminase 2. What causes these proteins to transform from ones that have an important physiological role into one that's associated with these disease pathology? What causes these proteins to go rogue? Why doesn't everybody get Parkinson's or Alzheimer's? We all have alpha-syn, we all have tau, we all have TG2, we need them. So why doesn't this happen with everybody? Our lab uses a lot of biophysical techniques, we use kinetics, we use a lot of protein chemistry work, and now we're actually starting to get in a little bit of clinical proteomics works too, so we can start looking for early stage biomarkers. So as much as we can do to start looking and figuring out how these diseases work. So the star of today's show, though, is transglutaminase. So when we talk about these transglutaminases, these enzymes are actually called nature's biological glues. So they will take a glutamine-containing substrate, they will catalyze in a calcium-dependent manner. They will take that and they'll form this acyl enzyme, thioester intermediate. So this is conserved across the family of this catalytic triad. And then, depending on what that second substrate is coming in, if it's water, it's actually going to take this glutamine substrate and deamidate it. It is going to make an isopeptide bond if you have a polyamine or a catecholamine, or important for neurodegenerative diseases, it's going to cross-link two proteins together. So it'll take this reactive glutamine and cross-link it with a reactive lysine, so you get this gamma-glutamal-lysine bond. So all three of these reactions, the transglutaminase family can actually catalyze. So this is the canonical calcium-dependent TG family reaction. So TG2 is the one that we're going to talk about today. So this is one of the structures, crystal structures of TG2. There's 7 members in the family, 8 members in the family, TGs 1 through 7, very creative with the names. Factor 13X, which is factor 13A, if you know anything about coagulation, in the coagulation family. And then there is protein 4.2, which has no transamidase activity, but looks a heck of a lot like this, okay? So TG2 looks a lot like, has the same global architecture as these other transglutaminases. However, it's the rebel of the family. TG2 is ubiquitously expressed. It's everywhere. It's everywhere and anywhere that you can think of it. So they often call it tissue transglutaminase because that's where they first found it. It's in muscles, it's in neurons, it's in macrophages, it's in microglia, it's in the endothelium. You'll find it in the cell surface, the nucleus, the mitochondria, cytoplasm, the plasma membrane, the extracellular matrix. It is everywhere. TG2 has a very low substrate specificity. So all of the other isoforms only will catalyze those reactions on a few select substrates. The most are 3 or 4. When you look at TG2, there are over 200 verified substrates just for those cross-linking reactions. The glutamine or the lysine residues have to be in, or are preferred to be in, intrinsically disordered proteins or proteins that have an intrinsically disordered region. And that's unique to TG2. The other transglutaminases, they really don't care where it is. But for TG2, definitely needs to be in there. Higher than predicted number of substrates that are intrinsically disordered. TG2 is also a multifunctional. So you can do that transamidase reaction. It's also a G protein. It's also GTPase activity. It's protein disulfide isomerase. It has serine threonine kinase activity. It acts as a scaffolding protein. And there was just a paper that came out as a preprint yesterday that showed it was also an RNA binding protein. On top of being everywhere, on top of having a bunch of substrates that it likes to touch and do stuff to, now I've got an enzyme that does all these different things on top of it, which makes life really interesting in the lab and makes students oh so happy when they come through it. What we're really going to focus on today, though, are these 2 activities, this calcium-dependent transamidase and this G protein or GTPase activity. So, of course, because it's everywhere and it does everything, it's going to have a lot of physiological roles, right? So proliferation, apoptosis, adhesion, migration, wound healing, inflammation. So tons of roles that we need in it. But there's also a bunch of stuff that TG2 does that we don't want it to do, okay? And again, we're focusing on those 2 GTPase activities and then the canonical activity. So for the GTPase activity, we know it's been associated with colorectal cancer. It's been associated with pancreatic cancer and then triple negative breast cancer. So overexpression, overactivity of TG2 and its GTPase activity is all associated with cancer. Okay, and poor prognosis, poor outcomes, more proliferation, more aggressive cancer. On the flip side, TG2's canonical calcium activity is all associated with neuroinflammation and neurodegenerative diseases. Okay, so we're looking at amyloid beta aggregations. We're looking at the neuroinflammation. We've seen it in Alzheimer's, we've seen it in Parkinson's, and it's actually a therapeutic target now for both cancer and neurological conditions. However, all of the drug trials that have been going on have been failed, right? They have failed miserably. They think they find targets, they think everything is great, and they have just failed absolutely miserably once they get past a certain level. Usually they get it into the mouse point and then they're done, okay? And one of the reasons, hopefully I'll convince you by the end, is that the model that they're looking at to describe TG2's activity is all based on what they think is going on for the TG family, which I just told you, TG2 is the total rebel of the family. But people are making these comparisons. So when you look at the crystal structures that are known, again, we've heard earlier, you have to know your structure, but you also have to be able to trust your crystal structures, right? So what's known is that the TG2 makes this elongated structure. So we have the beta sandwich domain along with the catalytic core. It goes into a linker region that's not shown or seen in the elongated structure, beta barrel 1, and then you go into beta barrel 2. All of these elongated structures that have been solved for TG2 are what's known as their calcium binding structures, even though there's no calcium that is bound in the structure. That's calcium, usually crystallized with 1 to 5 millimolar calcium, and there should be 6 calcium binding sites. And all of those structures do have some sort of covalently bound peptide mimic inhibitor that's locked right into this active site cysteine. So those are our nice elongated structures that are representing the calcium bound structures. Then we have the nucleotide bound ones. So this is a nice compact structure, right? So the nucleotide fold, the nucleotide binds here, and this is in between beta barrel 1, catalytic core. This is a non-canonical GTP binding or nucleotide binding domain. No magnesium is required. It does not have a grasp fold. It has a whole bunch of arginines and lysines in there. You can just bind the GTP in there, or GDP or ATP. Okay, so the whole idea in this now is based on how all these other transglutaminases work, and these couple of crystal structures, and some data that's been really gotten using non-natural substrates. So we're using things like CBZ gly. I should say they, not we. They're using things like CBZ gly or some sort of mimic, right? So they're not actually using full-length substrates, protein substrates, because it's kind of hard to do that, but we'll show you it can be done. In the cell, in order to get transamidase activity, you have to have all 6 calcium bound first. Once those calcium bind, you open up, you stabilize the enzyme. Once that enzyme is stabilized with the 6 bound calcium, you can then bind substrate here. You can get transamidase activity. On the flip side, when GTP binds, closes this enzyme down. So it will bind back here. Those 2 beta barrels flip around. You get a translation, huge domain movement, translates, close, and now you have GTPase activity effectively inhibiting the transamidase activity. Based on concentrations in the cell, the apparent Km that was determined for calcium that was determined with these really crappy substrate, yes, it was, yes, of 2 millimolar, and the GTP KD of approximately 0.15 micromolar. People have surmised that TG2 is not active in the cell as a transamidase unless you are under stress. Extracellularly, oh, that's fine. Intracellular, nope, not happening. Flip side, it's only going to act as a GTPase. So this is the basis and the kind of model that everybody has been using for everything now, to design the cancer drugs, to design celiac-based drugs, because this is important in celiac disease, and to look at the neurodegenerative diseases as well. However, they also forgot that I told you there was redox coming, but there's a redox-sensitive allosteric disulfide bonds, okay? And this allosteric redox-sensitive disulfide bond is right here near the active site, and you can see this 370, 371 here, forms the bond in one of the crystal structures. And they also know that the cysteine 230 kind of acts as a vehicle to flip things back and forth. Okay, so it's allosteric disulfide that's only needed to help control activity. Why do we say that? Because we actually say that the transamidase activity needs to be fully reduced for it to be active. Okay, and that's shown. So why do we think all of this is wrong, besides the data I'm going to show you? Well, we know that there's products from TG2's transamidase activity, routinely found in vivo all the time. These in vitro assays have really relied on the non-natural substrates. All of the calcium-based assays that have been done so far, HDX, some of the gel-based assays, anything that's been done up until now have been done in the presence of those covalently bound inhibitors. So because TG2 will cross-link itself, okay, but we found a way around that. So you're really looking, though, not at just calcium binding anymore, right? You're looking at the mimic plus the calcium. So we found a way around that, and I'll show you guys that in a little bit. And again, the full-length crystal structure with natural substrates or calcium is not available. The one structure that has calcium in, those two beta barrels, not there, too wiggly. And we'll talk about that in a few minutes too. Okay, so our big question, can we really assume that this thing behaves like a canonical transamidase? This is work, everything I'm going to show you today too is just about everything is unpublished from our lab. And I'll show you other people who have worked on it because this has been a labor of love. Every time we think we have a question answered, there's like 10 more because there are things that we try to follow in the literature and then we find out, nope, that's not right. We are using alpha-synuclein as our substrate. This is all recombinant work, right? So we make our own recombinant TG2, we make our own recombinant alpha-synuclein, and we've just started working with both beta and gamma-synuclein as well. The reason that we're doing that is because we do want to see how some of that substrate disorder actually affects catalysis and some of the movement and things with TG2. So we're really trying to poke it, bang it. Actually, we're trying to bang it over the head with a hammer and figure out what's going on. But really for us, the big one when we're looking at any sort of drug design or how this is working in neurodegenerative disease is using this alpha-syn. So we can tell by CD from what we're measuring and what we're looking at, all of our alpha-synucleins, all of these are monomers, which is really hard when you're making recombinant proteins for the IDPs and the IDPs is getting them consistently monomeric, not, so we see these coming out as a random coil. So, and I should mention, we do use applied photophysics. So we've been running these on all of the CDs that we have there. So we get random coils for all three. And what we see is when we react these with TG2, we can actually see we get some higher molecular weight oligomers. And then we actually see low molecular weight, whether that's some sort of deamidation that's making these more compact structures. We're not sure yet. We're still doing the mass spec to figure out what the modifications are, but we know that all three are substrates. And we're running these gels at roughly 10 to 20 micromolar calcium when people were running the reactions with the non-natural substrates of 5 to 10 millimolar, right? Because remember that apparent KM was 2 millimolar. So now we're starting to get closer to where calcium levels are going to be. We're still pushing them. We're still a little off. If we run just straight kinetics with alpha-synuclein, we can get an apparent Ka, Km of roughly 175 to 250 micromolar. I guarantee you that's still going to be lower though, because we have multiple reactions going on in here. We're just measuring one. So it's actually probably a lot lower, that apparent Km. This is just for the one reaction we're measuring. We can get apparent Km for alpha-syn of 1. But again, there's multiple residues on there that can be cross-linked, that can be active. We're just treating it all as one. So again, that's probably a little bit lower. So we know we can catalyze nucleons at low calcium concentration. Can we bind in the absence of calcium? So remember the whole idea of this reaction was 6 calcium have to bind. We open up the TG2, that nice elongated substrate binds, and then we go. We can bind substrates just fine without having any calcium around. So we take our enzyme, we dialyze it against 10 millimolar EGTA to pull anything that's bound to the TG2. We run everything under Keylexed water. So we've done SPR with the alpha-synuclein, and we can tell that when we start fitting these, this is actually to a 2-site model. So the alpha-syn initially binds, and then there seems to be a conformational change, which then sets that structure, so slow conformational change. We're still working on doing this with beta and gamma syn, but we have some initial CD structures. So if you look here, all of these are for the addition spectra, so just either the TG2 alone spectra or the beta or gamma syn spectra alone. If we just added them, this is what it would look like. And what we see is when we titrate in different amounts of alpha syn, we see slightly different spectra. So we're presuming that we're forming some sort of complex. We actually do have HDX2 for the beta syn, but I'm not going to show that yet. We know we can bind now in the absence of calcium. Okay, so that kind of throws this whole allosteric mechanism out the window, right? We don't necessarily need calcium to bind first to kind of regulate this whole thing. We need it to run the reaction, but not to actually allosterically regulate the enzyme. So what's going on? But what if it's acting more like a hub protein, right? So when we think about hub proteins, we think about proteins that have combined with a low specificity, right? So they'll bind a whole bunch of substrates, fairly low specificity. They're inherently flexible. They have intrinsically disordered regions on their own. They're allosterically regulated, right? And they can bind quickly, turn something over, and they can basically process a lot of information all at once. Well, if we started looking at TG2's intrinsically predicted, intrinsically disordered regions, which are just highlighted here in salmon. Let's go with salmon at this point. And so what we saw, if you look here, so this is just now on this elongated structure, and then this compact structure here, you can see where we've mapped those regions. Again, these structures are substrate bound structures, right? So yes, you will probably see intrinsically disordered regions that are stabilized in these structures because we do have some sort of substrate bound. What's interesting to note is that a lot of these intrinsically disordered regions actually are directly overlaying or near the calcium predicted calcium binding sites. So we went one step further and said, well, what does those structures look like, right? So we started looking then at these global B factors and the normalized B factors for each residue from all the open structures and all the closed structures. And we overlaid that then just with the intrinsically disordered regions. And what we found, anything in gray are missing regions from the structure, which are fairly consistent across the board for this elongated open. Anything bright yellow is going to be something that has a really high normalized B factor. So again, in the crystal structure, you can assume that that's going to be fairly wiggly. Anything that's a black or a dark purple is going to be fairly solid, right? The global B factors alone are anywhere between 45 to 60 for these structures. Now that'd be fine if we were talking about structures that were 5 angstrom, 6 angstrom, or structures of things that were really, really big. Now TG2 is 79 kilodaltons, so it's bigger, but it's not one of these megadalton proteins, right? So we're talking resolution of 2 to 3 angstroms. We're talking about a 79 kilodalton protein. So these should not be that high if that protein is not wiggly, even in the crystal structure. And these are just mapped onto the open and the closed, so you can kind of see where they are. So again, up here, and this will be important when we talk about HDX in a few minutes, and then back on the closed. So one of the things, though, that really bothered us was that all of the published literature showed 2 conformations, which everybody said, well, it's open and closed, calcium GTP bound, that's it, we're done. Because they ran these dang native pages, which turned out to be the bane of our existence for a little bit. So they would take 4 to 20% gradient native page shells, run everything at 2.5 micromolar TG2, and they would see 2 bands. Great. And that was every paper that ever ran those conditions. I don't always follow the rules, so first thing I said was, we'll start upping the concentration. Let's just see what happens. As soon as we started increasing the concentration, we started seeing some smearing. We actually started seeing some more bands. Now, we've run these a couple times in a couple of cups to show that it is not degradation bands. Okay, so these are still full length. And we actually plotted then, if we took the relative fractional, the RF values, we plotted across the board versus TG2. You can see there's not much difference So these aren't from dimerization. There's not a concentration dependence really on this normalized, once we normalize the density for the amount of protein. Right, so this is not a monomer dimer formation. These are, the bands are just getting darker because we're putting more protein on. So because we're an academic lab and we ran out of 420 gels, and they're really expensive, I told my students, I said, well, just pour 12%. Let's see what happens. Just pour 12% native gel, go run it. And we got this. And I was like, well, something's wrong. Go run another 12% gel and see what happens. And so we did this. So we found that really running these gradient gels, so again, here's the 2.5, here's the 2.5, where everybody runs all their stuff. When we started running these non-gradient gels, we could actually get things to separate. Okay, so we can get what we believe is multiple conformations now to separate. So we can see these different populations that are coming up. So we have a more compact population running through here, and then we have several of these that are not as compact. So this is just the APO, okay? And again, same thing when we're looking at this, that we do not have any monomer or dimerization going on. So we threw in some calcium, again, very TG2, threw in some calcium, and then we threw in some GTP. If these things are wiggly still, if we bind ligand and we're still pretty wiggly, we should be seeing multiple conformations come up. And one of the things that we realized we could do is if we use BSA as kind of our standard for how far down on a gel it would go for our RF standard, we could normalize all these relative RFs to that BSA, right? So we didn't use it as a molecular weight marker. We used it basically as just our front. So we could take every peak for every band on all of these different gels and normalize it to where the BSA ran, for how long it ran, because we need to separate different. If we plot that, the relative RF values, so 0 is BSA, where that runs, you can actually see, so this is the native, nothing's in there, so 1 millimolar EGTA. We can see the calcium actually has 2 bands that run at the same front. The GTP does not, and then the calcium also has some higher up bands there. Okay, so we have these bands that are the same with the calcium, so populations that are the same, but then some that aren't as well when we add that calcium is in there. So we're getting different conformations, we're getting different populations. When we're adding the calcium, it's not as strong as it's expected to be completely open, like they say they should be. And in fact, when we start looking at CD, we do see some differences. However, if we start titrating in either GTP or calcium, we use calcium bromide instead so that we could actually see further down. We weren't seeing huge differences in changes in secondary structure. If you notice a big white space, I took out the best Sully predictions that we had in there earlier. So we won't talk about those. We'll see those later too. But really, when you actually did it that way, just as a comparison, there wasn't any differences. As a qualitative comparison, there's really not that many differences. That's what we're going to go with at this moment. What's interesting, though, is like you can take the PDB and do a prediction and do an actual, like, this is what it should look like. And it overlays perfectly with the GTP. The reason the calcium one looks a little weird, we can talk about it some other point, but that is, we think, a buffer effect because TG2 likes MOPS and sulfate-containing buffers. But that's a whole nother hour-long talk. So we did differential scanning fluorimetry. So these are those thermal unfoldings, Cipro binds, right? So we put them in. This is the aggregation point here. So we can get thermal, we can get our TMs, our melting temperatures, and there's a way to extract estimates of thermodynamic parameters, right? If you keep your numbers right down here, you can get an estimate, okay? Not perfect, not great, but it gives us a rough idea of what's going on. As you can see, as we're titrating in calcium, absolutely no change, and this is no different than the wild type. When we start titrating in GTP gamma S, which we know from other studies, but it's just like GTP, we can actually see a huge shift in the TM as well as a decrease in the overall fluorescence, which means something's going on that the Cipro isn't binding as much. If we do our estimates here, we see there's probably about an 8-degree change for the GTP gamma S melting temperature. So it increases, so it shifts to the right. Again, really, really, really rough estimates, but it gives us a rough idea to go off of. Here we actually see an increase in the delta G for unfolding, no change in the delta S. And we see that increase in that unfolding enthalpy as we're going up with the GTP gamma S. So again, we can use this differential scanning, this DSF, to give us a rough idea of not just that TM shift, but a look at what's actually going on too, right? So if we see these huge increases in CIPRO binding and fluorescence, we know we're exposing more hydrophobic regions versus some of the other ones. We did some HT exchange mass spec to show that these are also, the APO enzyme is also very wiggly. Within 10 seconds, we see roughly 30% exchange in some of those intrinsically disordered regions. This is 2 hours exposure. So this again is relative fractional uptake. So you can see this whole protein is just dynamic. We know it's folded still under these conditions. We've checked. So we know it's folded. We know we're still moving around okay. We know it's properly folded. We've checked activities. What happens when we throw that GTP and that calcium in there? Well, if you would expect, if calcium is actually binding to its sites, that we would have nice bright red spots after 2 hours. And we have this one really odd red spot, which is nowhere near any of the calcium binding sites because those are all in here. So we have this nice, big, huge red stripe somewhere, and it consistently shows up there. But none of those calcium binding sites that we would expect to be showing up are showing up. If this enzyme is truly binding calcium the way it says it should be binding calcium and having all of these effects the way it should be. Same thing with GTP. We do see GTP binding. We see a nice dark blue GTP binding site right where the residues we know are, but the rest of the protein, not that much, which is really consistent with some of the other things that we've seen, is that this binding of the calcium does not do what everybody thinks it does. And the binding of the GTP, it's actually not this big solid chunk, and it's still wiggling around a whole bunch. We really think this is acting, the calcium at least is acting like the S100A proteins, where you bind the substrate first, and then the calcium comes in and locks things down. Okay, so we think like all the binding that we do see is non-specific calcium binding at this point. So we get some binding, but it's nothing that's really going to promote catalysis. The GTP, and what I didn't really mention is there's a lot of other proteins that will bind to TG2 to help this GTPase. PLC delta 1 is one of them. We actually have calreticulin that comes in as the other part of the G proteins. So we might see once we get that second protein coming in, things lock down. But again, this whole idea of this regulatory mechanism is not what it says it's going on. And all of the drugs that are being designed right now are going based on this mechanism. I promised you redox, so I'm going to show one slide on redox because there's a whole nother layer of this too. There's that redox sensitive disulfide, allosteric disulfide bond. So the transamidase activity is only active as under reducing conditions. And nobody's actually ever checked to see if the GTPase activity is actually more favored under oxidizing conditions or not. If one is reduced, you would think the other is oxidizing. We started working on this a little bit, and what we've seen so far is that this GTPase activity is preferred to be under oxidative conditions. We haven't confirmed it all yet, but it'll work under reducing conditions, but we prefer it to be under oxidizing. What we wanted to do, though, is actually look and see what happens to the protein. So we hit it over the head again with a hammer. I mean, we reduced the hell out of it, and we oxidized the hell out of it, right? This is nowhere near physiological, but we want to make sure everything was pretty much oxidized and reduced. So we hit it with either 1 millimolar TSEP. Again, TSEP's a little bit better than DGT at this point. It'll reduce everything. We can heat it up. We're good. And then 2 millimolar GSSG. Again, we're looking same sort of thing. This is just our native, so we didn't reduce or oxidize. We do purify under semi-reducing conditions. However, we had dialyzed everything away and just kind of let the protein sit out before we did anything. Again, we can look at our DSF. So this is CIPRO binding as a function of increasing temperature. We can look at fluorescence changes as well as that shift in the TM. And we can get really, 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 really rough on delta G's for unfolding, but what's really important too is this melting temperature. So for GSSG, we're at about 49. We go up slightly with TS or TSEP, and we can see we're at 50. So there's a slight change in that. But what's more important, really, I think, is this change in fluorescence intensity. So the CIPRO binding, which means it's, again, binding the hydrophobic patches as you start unfolding that enzyme with temperature. And we see that that's completely different, right? So if we have that GSSG in there versus TSEP or even that native protein, we're getting a lot lower fluorescence intensity. So it means hydrophobic patches we think are totally different or being exposed differently. Some sort of conformational change may be going on that they're not being exposed as much. And again, really rough estimate of the delta G for unfolding. We can see that these are also slightly different. So really, what do we think is going on? Well, we know it contains IDRs. We know it's inherently flexible. We know it samples multiple conformations in its native state ensemble. We know it has this redox-sensitive allosteric disulfide bond, at least this one set. We think that then these redox bonds actually determine kind of the population of the ensembles, right? So we think that these redox are going to determine, is TG2 going to be a transamidase, or is it going to be a GTPase, all by shifting what conformations there are. Okay, so if it's transamidase, it's going to favor more reducing conditions. GTPase is going to favor more oxidizing conditions. And then that's going to facilitate those ensembles, right? Whether we're going one way or the other, is really going to facilitate what type of substrates it binds. Whether it's going to bind those substrates that are for transamidase, alpha-syn, beta-syn, gamma-syn, or those substrates that are more associated with GTPase activity, right? So it's the redox driving the ensemble population to begin with, and then that binding the substrates, and then in fuzzy complexes, and then the allosteric ligands coming in and locking everything down. So we've given you the brief. There's a lot more data that we haven't shown yet, because when you're going through this and kind of beating the head against the wall and doing multiple things, which is why so many people are on this list, we really have been kind of running through this over the past couple of years. Whitney Bond and Mithil and Ansley Reed are the three in there right now who are really focused on this project. So, but there's been many over the year who have done all of this. And then we actually did get money from Parkinson's to do this, as well as the Brody Brothers research to continue on. Hopefully, we propose this next to the NSF and continue on from there. They like it as well. But this is where we're taking our redox, allosteric, protein motions, IDRs, IDPs, and understanding the structure to actually design the drugs. Because this is why we still think people haven't been able to get those drugs that quite work yet.